A quick nomenclature review here. So magnesium hydroxide, what was this one? O2 is oxygen. SO2 is sulfite or no? What is sulfite? So, what's the formula for sulfite? Well, it depends on what sulfate is. What's sulfate's formula? SO4 minus. So sulfite would be SO3 charge. That's sulfite. And so this is not sulfite. Nor is this. We don't call this sulfite because what's missing? The charge. So this is called sulfur trioxide. Sulfur, and therefore this one would be called sulfur dioxide gas. But, you know, when I look at the label on wine, let's say sulfites in wine, you know, wine, this contains sulfites. Is that sulfite? No, that is sulfur dioxide. So why are they calling sulfur dioxide sulfite? I don't know. But I do know something. I know that sulfur dioxide, I know why they use sulfur dioxide instead of sulfite. They use sulfur dioxide instead of sulfite because they'd have to use a salt, like sodium sulfite. If we use sodium sulfite, the sodium ions are going to give taste to the wine because, you know, sodium ions have a salty taste. And so the sodium ion, they probably don't want to use sodium sulfite because that's going to change the flavor. And so they're going to use sulfur dioxide instead. Is that fair? Well, what's the purpose of the sulfites? The purpose of the sulfites in wine are to act as an to be oxidized, antioxidant. And so what is the oxidation state on sulfur here? +4. What is the oxidation state on sulfur here? +4. So actually sulfite and sulfur dioxide are going to have very similar redox properties because sulfur is both of these +4. And so the reason I think they use sulfites instead of sulfur dioxide is, one, sulfur dioxide sounds like a very toxic gas. And when people look it up, when people look up sulfur dioxide, what are they going to see? People are going to see stuff like this. Inhaling sulfur dioxide is associated with increased respiratory symptoms, etc. They're going to see that sulfur dioxide looks like it's poisonous.
Where does it come from?
Sulfur dioxide?
Yeah.
Where does it come from? They make it. You can make it.
So it's like a chemical.
Yeah, it's like. In the U.S., you know, ingestion of it lists the two food preservatives, sulfur dioxide and sodium bisulfite, as being safe for human consumption, except for certain asthmatic individuals may be sensitive to them in large quantities. These are sulfiting agents, you know, including sulfur dioxide. Sulfiting agents because of the. So maybe it sounds better, you know, rather than sulfur dioxide, maybe you call it sulfite because it has the same like redox properties. Both of the sulfurs are +4. And so that's where there could be some confusion in this. When you look at sulfite, it doesn't sound as bad. Sulfur dioxide in volcano, this is a Hawaiian. And in fact, in Hawaii, they had to evacuate because large concentration of sulfur dioxide of that, of course. A lot of SO2 emitted from volcanoes. Anyway. Let's kind of change. quick review. KHSO4.
Potassium hydrogen sulfate.
Good. Another name. Give me another name for that. Potassium hydrogen sulfate or it's kind of like sulfuric, but it's not. We call it potassium hydrogen sulfate or old name. It's not really old name. It's still used. Like hydrogen carbonate has another name. What's another name for hydrogen carbonate? It's actually more common than hydrogen carbonate. Yeah, bicarbonate. In fact, if you look at the ingredients of baking soda, they never say sodium hydrogen carbonate, they just say sodium bicarbonate. And so this is called potassium bisulfate. That's the other name for this. Bi indicates the hydrogen. What's this? Yeah, we should be at the point where these should be automatic. We wouldn't, let's say this were aqueous. If this were aqueous, we'd call it phosphoric acid. Nobody ever calls this hydrogen phosphate. Everybody calls this phosphoric acid, whether it's pure in liquid form or a solution in aqueous form. This one? Ammonium chloride. Ammonium chloride is quite a bit different than ammonium nitrate. Tell me one differences. What's so dangerous about ammonium nitrate? Reducer and oxidizer are the same thing. Ammonium chloride, we don't have to worry. This stuff is stable. Ammonium is a what? Reducer or oxidizer? Reducer. And chloride is a, chlorine is an oxidizer. Chloride is a reducer. So this is a reducer and a reducer. It's no big deal. It's stable. This is ammonia. Now here we have two names. If this were pure, we call it hydrogen chloride. Or if it's an aqueous solution, we call it hydrofluoric acid. Whereas this one is always called phosphoric acid no matter what. People just call this phosphoric acid. This would be hydrogen chloride or hydrochloric acid. This would be magnesium hydroxide. We already saw that up there. Hydrobromic acid or hydrogen bromide. Hydrogen, bromine, sodium sulfate, sodium hydroxide, sulfuric acid. Nobody ever calls this hydrogen sulfate. Everybody calls this sulfuric acid no matter what.
Can you explain why chloride is not a reducer?
Why chloride is a reducer?
Because I was associating the minus with oxidizer and plus with reducer.
No, never associate charge. Minus is, don't associate it that way. You're associating minus with oxidizer, like nitrate. No, I never associate minus with, I usually associate minus with reducer, not with oxidizer. The reason this is an oxidizer is because of nitrogen. Oxygen's happy, as is. Oxygen wants these two electrons, and it's fairly stable like that. Nitrogen is unhappy. And so I associate this because I see a large positive charge. I don't, it's going to add up. This net negative charge is because of oxygen. But oxygen's happy. There's an imbalance of positive and negative charge here. The oxygen's happy as is. So when I think about chloride, chloride, okay, if chloride's an oxidizer, it takes electrons. So if you associate an oxidizer with negative, then this is going to form chloride with a 2- charge. And so when I look at this, do I think, does chloride want another electron like oxygen? Or does chloride just want one electron?
Just one.
Yeah, just one. And so this doesn't happen like this. In other words, with chloride, two chlorides can lose electron to go to chlorine plus 2 electrons here. And so this net charge, we have to be careful. The net charge is the sum total of all the oxidation states here. When we total them up, we get the net charge. The net charge is not what we look at unless we're looking at the charge on the individual atoms. Now this net charge is the same as the oxidation state because there's only one atom. And so when I see that the atom has a negative charge, then the only thing it can do is it can be a reducer. Like all these oxygens, the only thing they can do is be a reducer. That's it. They can't be, they aren't going to take another electron. And so the association is not with the net charge. There's no clear correlation with that. If you look at the net charge, if you look for the pattern here, this is what we do. Scientists look for patterns. And so the only way you can see patterns is by looking at the data. The only way you can look at the data is work. It's a lot of work to look for these patterns. Zero charge, negative charge, zero charge, negative charge, zero, zero, negative, zero, zero. So what's the pattern so far? It's either neutral or negative. But then we go here. Positive, positive, neutral, 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 positive. Is there a pattern there that you see for the net charge? And these are all oxidizers here. There's no pattern. The pattern is when we look at the oxidation states and then look at that, what they want to do as far as the oxidation states go. That's where the pattern comes in. And so normally it's associated. Oxidizers have a positive oxidation state or neutral oxidation state. Like oxygen is neutral, 0, and it wants electrons. Fluorine is neutral, 0, and it wants electrons. Or iron 3 is positive and it wants electrons, but never negative, unless it's like peroxide. Peroxide is one of the few species that are going to be negative. And so if we look at hydrogen peroxide can also be an oxidizer. It's because the oxygen is -1. And so here's a negative where it can take an electron because oxygen doesn't want to be -1, it wants to be -2. So this is a negative species. But there's not a direct correlation. And in fact, between. So we'll see that as we go along. So this is a question I always ask on tests. This is a question I always ask on tests. Ammonium is electron rich. Why? It's got a positive charge. How can ammonium be electron rich when it has a positive charge?
Because nitrogen can give an electron.
Yeah. It's because, okay, that's a net charge, but when we look at the individual charges, hydrogen's okay at +1. The electron richness comes from nitrogen and being, what's the charge on nitrogen? -3. And then when we sum up all these charges, we get the net charge of +1. There's an imbalance. So 3 of these positive charges are going to be canceled out by this negative, leaving 1 positive charge not balanced out. Nitrate is electron poor. It's electron poor even though it has it seems like it has an extra electron, doesn't it? But that negative charge is a result of the imbalance. This negative charge is not, it doesn't have an extra electron. Do you think that, which one of those oxygens has an extra electron that wants it to give it up? Which one of those oxygens has an extra electron that it wants to give away? Do you see an extra electron there? No, that negative charge is a result of an imbalance of positive and negative charge. Nitrate is electron poor, even though with a negative charge. Ammonium is electron rich, even with a positive charge on there. And so the positive and negative charge, we have to analyze it further, otherwise there's no strict correlation between those. But ammonium chloride, both are reducers. You can see where chloride's a reducer. When you look for chloride on the chart, it's here. Chloride is a very weak reducer. It's pretty unreactive, right there. There's no chloride on the oxidizer side. There's chlorine on the oxidizer side, but no chloride. Of course, this is good stuff to review because we're having the test on redox coming up next. Plus other stuff. Anyway, let's move on here. So we did magnesium. This one, magnesium nitrate. I think we did this one. What's this one? Sulfuric acid. So again, nobody calls this hydrogen sulfate. Everybody calls it sulfuric acid. Sulfur. Okay, is that zinc 2 or is that just zinc chloride? And so if we look at the periodic table, it looks like we would use a Roman numeral for that because it occurs in this region. We always use a Roman numeral, except for a little island of elements. What island of elements do we?
Zinc, cadmium.
Yeah, this little elbow, zinc, cadmium, and silver are the only 3 that we do not use Roman numerals for. And so zinc's, these are the pseudo group 1 and pseudo group 2. You know, group 1 is always +1, group 2 is always +2. In the pseudo group 1, these are +1, and the pseudo group 2, these are +2. Zinc is always +2. There's no variable charge, so we don't need the Roman numeral. It's just called zinc. Chloride. What's CaCO3? Calcium carbonate. CaO. Calcium oxide. We know CO2 is dioxide. These are repeats. BaCl2. Na2CrO4, sodium chromate, BaCrO4, barium chromate, lots of repeats here. So let's just go down here. Ca3PO4, 2, calcium phosphate, CaNO3, 2, calcium nitrate, Na3PO4, sodium phosphate, I think we already did that, sodium chloride, yeah, silver nitrate, silver chloride. Those are very common compounds that we see quite a lot. And so that's chapter 10. Chapter 10 deals with this.
For the, I know when you have a single oxygen, sometimes it's superoxide. When do you use that?
Superoxide? It's very rare that we see, because superoxide is pretty unstable. So if you tried to buy a bottle of superoxide, it'd probably decompose. It's not going to last very long. Superoxide is produced in your body. And so superoxide is an oxidizer that's produced in your body, so you want antioxidants. Your body has natural antioxidants. And so the only time you'll see superoxide is when you get the weird compound that looks like this. This is an O2 with a -1 charge. It's superoxide. We also see we also see other weird compounds. Another weird compound that we see, and this is something that people, I think, wrote on the exam, is magnetite. Magnetite is a mineral. Minerals are compounds, and this mineral is Fe3O4. Fe3O4, what's the charge on iron? So I think, Anna, you were asking about this trick, right? One of the tricks that people do is they just use these as the charges, right? And so they get Fe4 plus O3 minus. Does that seem to make sense? No, this trick doesn't work for this compound. So you might go, well, maybe that's a peroxide. you know, because it doesn't have to be an oxide. So for example, when we're doing this, we have different charges on, so it could be an oxide. Yeah, so we have 4 of these kind of oxide type, oxygen with a 2 minus. Or it could be like a peroxide. A peroxide would have oxygen in the -1, so we have 4 of peroxide type. Or we could have superoxide. Superoxide, each oxygen, because that's an O2 minus 1. O2 minus 1, that means each oxygen is minus 0.5. Well, how do you get that? Well, it has to do with the structure, which I'm going to talk about right now. But this would be superoxide. So this is oxide, peroxide, superoxide. That's what we have. And so that's going to change it. If all these are oxide type oxygens, then iron would be, well, we have 3 irons. And so what would iron's charge be? Well, this is sum totals to -8. This has to be +8. Balance out. And so each oxygen is going to be +8 thirds, +8 thirds, +8 thirds. And so this would be called iron, Roman numeral 8, divided by Roman numeral 3, oxide. Does that look right to you? Iron 8 thirds oxide? Oh, we get the same thing, same kind of weird thing happen here. It could be 4 thirds. Actually, these oxygens are going to be the -2, so we don't see this that much. The only time we see this is when the cation dictates. If we have variable charge, then we're always going to have oxygen in the -2, but if the cation dictates it, so for example like this, Na2O2, here, these cannot be O2 minuses. If these are O2 minuses, then the sodiums have to be +2. Is +2 a good charge for sodium? No, and so these has got to be oxygen to the -1. Sodium does not go to +2. It's the same thing with hydrogen peroxide. Hydrogen peroxide, each oxygen must be a -1, and each hydrogen must be a +1. Otherwise, it doesn't work. We can't go to +2 with hydrogen either. And so some things we can't go. Well, this is variable charge, so we can go. And so magnetite, this is wrong. This is not magnetite. You know what magnetite is? Magnetite is this. It's Fe3O4, and we have 4 oxygens at -2. And then we have irons. And these irons have to add up to +8. This has to add up to -8. The way to get the irons to add up to +8 is we get 2 iron 3 pluses and 1 iron 2 plus. So if we have 2 iron 3s and 1 iron 2, that adds up to 8. So this is a mixed cation salt. We have iron 3s and iron 2s in this compound. It's magnetite. Time. I got to start the next chapter. Let me just tell you what the next chapter is about. The next chapter is about atomic theory. We already did atomic theory, but we're going to do a much more detailed atomic theory. This is going to be quantum, the theory of the atom is quantum mechanics, or the quantum model. This is chapter 11, quantum mechanics, or quantum theory, or quantum chemistry, or quantum model of the atom. So we're going to look at the atoms, atomic theory in general, because so far when we're doing all this chemistry stuff, all this stuff is pattern-based. You know, we're figuring out the properties, ammonium nitrate, whatever else. We're figuring those out based on patterns and a little bit of theory. And so what we're going to do is we're going to dig deeper into the theory aspect, theoretical aspects of chemistry. So we'll start that tomorrow.